Uh, my name is Chris Winslow. I'm director of both the Ohio Sea Grant Program and Ohio State University's Stone Laboratory, also associated with LEARN, so the Lake Erie and Aquatic Research Network. What you've logged in for is our annual wetland monitoring update. You're going to hear some great talks on some of the progress that we've made through. If you're not familiar, this is an effort done by LEARN, and you'll hear about the Lake Erie and Aquatic Research Network here in a second. It is funded through the H2 Ohio program, more directly through the funding that the Ohio Department of Natural Resources provides. So I'm going to turn it over to Lauren Kinsman Costello to walk you through the presentation. We will be fielding questions as we go, so you can submit questions online. We also had some collected when people registered. So at the end of the webinar, I'll be facilitating the Q&A. Lauren.
Awesome. Thanks so much, Chris. And thanks to everybody who logged on. I'm Lauren Kinsman Costello. I am an associate professor at Kent State University, and I am the research lead of the H2 Ohio Wetland Monitoring Program. And I'm really excited to share this update with you all today. I know a lot of you have been following us since the early days and logged into this webinar every year, and some of you are new and first learning about the program. So I'll start with just like a really brief update and overview of what the monitoring program is, what our goals is, and then we're going to talk about one feature of the different things that we've learned so far and shared back with the ODNR and with our sort of wetland design and management partners. So hopefully this is useful to everybody. So why are we talking about wetlands? Odds are every single person logged into this webinar is not at all shocked and probably already tuned out looking at this intro slide, but to bring everybody up to the same page, we know that phosphorus loading, largely from the Maumee Basin, but throughout the Lake Erie watershed, drives recurring harmful algal blooms that are economically and ecologically impactful. And to address this issue in 2014, based on the best available research at the time, the International Joint Commission set a basin-wide goal of reducing phosphorus loading to Lake Erie by 40% to lessen harmful algal blooms. And if we reduce excess phosphorus loading to freshwater ecosystems throughout the state of Ohio and throughout the country, that also helps mitigate eutrophication and harmful algal blooms and similar challenges throughout that region. So to specifically address this problem, especially within the Maumee Basin, the state of Ohio, as part of the Maumee Total Maximum Daily Load, has set some targets because it's helpful when you have a goal to set a numeric target. Within this context, the specific target of enhancing non-point source sinks, within which wetland restoration is one approach to, the goal is to use that tool to remove about 92 metric tons of phosphorus, and that translates into about 200,000 pounds of phosphorus. Now, this is just for the western basin of Lake Erie, the Maumee watershed, but the reason why I'm sharing this target, this number, is because the way we talk about wetlands and water quality improvement, often we're thinking about the efficiency of individual wetlands to remove nutrients. But in this situation, the state of Ohio is investing in wetlands to meet this budgeting goal, the total amount of phosphorus not getting into Lake Erie. So it's good if each individual wetland is very good at removing phosphorus, but the true goal is to stop this much phosphorus from getting into the western basin of Lake Erie. And wetland restoration is one tool that the state is investing in to try and meet this target. So the other tools that the state is investing in, all of them together are being funded by the H2 Ohio initiative, started by Governor Mike DeWine in 2019. And today we're going to talk specifically about the wetlands that the Ohio Department of Natural Resources is investing in. And these are restoration, construction, enhancement projects throughout the state with an initial focus in the Maumee watershed. And they have been incredibly successful at getting wetland projects on the ground. So this slide that the ODNR shares with us is probably already out of date, but you can just tell that based on the numbers, there has been a substantial investment in restoring building wetlands. To date, they have over 195 individual wetland projects throughout the state that are ongoing, adding up to 16,000 acres of wetland habitat, which is a really impactful number. I recently was at a talk that added up all of the wetland acreages in mitigation banks throughout the state of Ohio, and that's a program that's been going on for decades now, and it's really similar. So the ODNR has really embarked on a pretty unprecedented scale of wetland restoration. But it leads us to a really important question, right? It's not the only tool that the state of Ohio is investing in, and not the only tool that managers and policymakers have at their disposal in trying to mitigate nutrient loads. And in terms of the available research, wetlands are one of the more uncertain tools. In fact, we know that sometimes wetlands, when they're built or restored on soils that have a legacy of past phosphorus input, can actually be a source of phosphorus to downstream systems. So the ODNR knew this, and they wanted to hold themselves accountable and learn whatever lessons they could from this unprecedented restoration program. And so they've turned to us, the Wetlands and Water Quality Research Group of the Lake Erie and Aquatic Research Network, to monitor wetlands. So for anybody unfamiliar, the Lake Erie and Aquatic Research Network is a network of researchers throughout Ohio and the Lake Erie Basin, from mostly universities, but also other kinds of agencies and institutions that are working together to collaborate on research related to water resources in the region. So I'm presenting on behalf of this group, the H2 Ohio Wetland Monitoring Program. We are a collaborating, coordinated group of over 30 faculty, staff, and students from 6 Ohio universities. And we have not only built a foundation with the investment that the Ohio Department of Natural Resources and the state of Ohio has put towards monitoring wetlands, but we've also gotten support from the Ohio Water Development Authority and the U.S. Environmental Protection Agency and the Ohio Department of Higher Education to expand our capacity to do this work, to monitor wetlands and take advantage of research opportunities. The goal of our program is twofold: to both assess the ability of wetland projects that the H2 Ohio Initiative has supported at removing nutrients, surveil for things like potential nutrient release, for both nitrogen and phosphorus, because we know both nutrients are important contributors to harmful algal bloom size and severity, but also to inform continued wetland restoration decisions. The way we do that, we can't obviously monitor all 195 wetland projects, and at a certain point, monitoring another project doesn't provide as much information as well-designed sampling from among this population of wetland projects. So we currently monitor about 40, maybe up to 45 now, projects throughout the state, projects that have been completed where construction is done and we've characterized them enough to know how to sample them to learn lessons about their functioning. And we do baseline monitoring of simple things like water level, the concentration of nutrients in surface water, and soil nutrient status. And then in a selection of representative projects, we intensively monitor them with really a broad suite of different kinds of more intensive data collection approaches. And our goal in these focal projects is not only to kind of just assess, are they working or are they not, but how are they working? How are they not working? And get the best nutrient budgets possible. So I've said this before, people who've logged into my presentations have heard this before, but we think about this as like for the what we call the non-focal projects, we're kind of taking the wetland's vital signs, right? We're measuring its temperature. Maybe we can see if it has a fever, but we're not able to tell anybody why the wetland might be sick. Whereas in these representative focal projects, we're doing like the full body scan. We're meeting our deductible that year. We're doing our best to learn the most that we can about how these projects work so that we can then build on that knowledge to make more educated assessments and estimates for the remainder of projects where we aren't able to collect as detailed data. If you want more details about how the program is structured and the kinds of things we measure and why we do that, it can all be found in our newly updated monitoring framework, which was just published, released this year. There's a link on the slide, and somebody will put a link in the chat soon if you want more details on that. That's all I'm going to give. We've been doing this now for 5 years, which is bonkers. In 2023, we were up to monitoring 29 projects, and in 2024, we monitored 34 projects. And this map is just showing you the geographic distribution of the projects that we have actually collected data at and monitored. The blue dots are those extensively monitored projects, and the stars represent those focal projects. In 2023 was the first year that we collected enough data to summarize and report that data out to the ODNR and to the public. And so I'm just going to give a quick overview of the early results that are in that report, but I want to invite anybody logging in who wants more detail to access that report for more details. So the take-home message for what we found in 2023 is that most of the projects that we monitored most of the time retained phosphorus. If you estimated all the nutrients that went in, and this actually held for nitrogen as well, though I'm not going to show those numbers, and all the nutrients going out, and you made some really reasonable assumptions about the functioning of each project, all of them did not let extra nutrients go downstream. So that is a positive. Of the 8 projects that we were able to get really good budget estimates, we estimate that they removed 0 to 10 pounds of phosphorus per acre. And those individual projects, it was 0 to 108 pounds for the whole area of the project. And this is just thinking about the amount of phosphorus that would have entered and not left the project in 2023. This doesn't account for the prevention of new phosphorus being added to the landscape if fertilizers are being used, or phosphorus that naturally leaves agricultural and other impacted landscapes just because of an accumulation there. So this is sort of that bonus treated phosphorus in 2023. They also removed nitrogen, but there was a lot of uncertainties. First of all, 2023 and actually 2024 turned out to be a really dry year. So what we don't know is how these and other projects would respond to wetter conditions. And one big piece of uncertainty that's even underlying the numbers that we presented in the 2023 annual report is how much area some of these wetland drains, particularly in landscapes that are drained by tile systems. So the specific numbers for those 8 projects are in the executive summary of this report. Please download it and let us know if you have any questions about the specific results that are presented here. Instead of digging into a laundry list of results that we presented in this report already, at today's webinar, we wanted to kind of zoom back out, because one really important feature of our monitoring program is we work really closely with our funders, the ODNR, and the stakeholders and partners that they represent, the decision makers, deciding how best to use the resources that the state has invested for mitigating nutrient load, and the managers who are actually implementing these projects on the ground. So we're going to talk about one aspect of something that we've learned that we're trying to feed back into the managers and decision makers' knowledge. And the big question that everybody asks is, well, what makes a wetland good at removing nutrients? What kind of wetland is really good? What should we be doing? What kind of projects should we be funding? What kind of landscape should I be looking at? What kind of parcel should I be trying to turn into a wetland? And that's a little bit about what this talk is going to start to answer. So let's just back up for a second. So I know this is a really busy slide. In the late 90s and early 2000s, I was definitely a scrapbooker, and I like to bring some of that aesthetic to my PowerPoint presentations. So don't pay attention to the details. This is just a bunch of different screenshots of wetland projects designs. I know lots of people who are watching this right now probably recognize a project that they worked on or that they've monitored. But what you can see here is each one of these kind of depicts the boundaries of a parcel, and you see the kinds of things that designers and managers can at least try and plan for and design into a wetland. You know, we can move earth, we can dig pools, we can plant plants, we can reroute water. I could make a really long list, and I actually did, of all these different features, but we don't have time to present that in this webinar. Have to be a different webinar. But just think about all the different things within the parcel boundaries. And the one thing in common that you see in all these designs is there's not much that we're seeing outside the parcel boundaries for each of these projects. This is what's going on in the boundaries of the system. And this is just a view of what these systems look like when they're built. You can see the pools, you can see the plants, you can see where earth moving was done. There's things you can't see, like whether or not a tile drain is entering them, or whether or not there's a pump controlling the water going into the site. The things that were pictured in those design plans and in the images, all of those things can promote the processes that help a wetland store nutrients, the physical, chemical, biological processes. I've presented in the past, and there's great background in the monitoring framework and elsewhere about how these processes work and the kinds of conditions that promote them. And again, that's another webinar that maybe we'll give in the future. But in the context of H2 Ohio, in the context of those TMDL goals, and the context of trying to mitigate nutrient loads to downstream systems, at the end of the day, budgeting is somewhat more important than the interior wetland process, right? You want less nutrients leaving that wetland than going in. And that is the end goal for the H2 Ohio initiative. So from a certain perspective, you can put all those arrows, that whole wetland, you can just slap it in a black box. You can measure everything going in, everything that's going out. And just like your bank account, you hope less leaves that goes in so that your net load reduction number is positive. So, and not negative, and maybe not zero. Zero means it's doing no harm. But if you're, spending lots and lots of money to build a wetland, I think the hope would that be that the number is positive and maybe pretty big. Conversely, if there are no nutrients going into the wetland, especially, then there's no nutrient load reduction. And this is a really important thing to consider in the policy context of H2 Ohio wetlands. So backing up, but still within this budgeting framework, how do wetland restorations prevent phosphorus from going downstream? How do we account for that? And there's kind of two buckets that we can count up pounds of phosphorus into. The first bucket is what we call phosphorus loss prevention. And this is the storage of phosphorus on the landscape that happens just because maybe you're taking a plot of land that was agricultural or a nutrient source of some kind, and you're preventing the loss of water from that site, right? So maybe we have a farm field, maybe it's tile drained. When you convert that land, when you disrupt the tile, you stop the drainage, that phosphorus then is not leaving that landscape. And on top of that, if there was fertilizer being applied, there's not new fertilizer being applied, of course. So this is great. This is what a lot of wetland restoration projects do. But what's even better is this second bucket of phosphorus load reduction, which we call phosphorus filtration. So that's if you can put this wetland downstream of existing phosphorus source landscapes, that phosphorus can then be trapped by that wetland. And this is the real goal of the investment that H2 Ohio is making. And what's critical for this goal is how that wetland is connected to the landscape. And so today, this is going to be the focus of our webinar is connectivity. That's why it's in a big, yellow, bright PowerPoint icon. So what do we mean by connectivity? This is a really common thing. Wetland ecologists think a lot about connectivity, but there's lots of different dimensions to this one word. So one dimension is, where does the water come from for a wetland, right? All wetlands have some combination of water coming from precipitation, surface water, and groundwater. And the amount of those different sources affects the chemistry of the wetland, and it affects the hydrology of the wetland. So those are really important features. Some of them, that water might be coming in from a stream, might be coming in from a tile drain, it might be coming in from a storm drain. Those kinds of things greatly affect the chemistry of the water and the way it's connected to the landscape. One really important question with connectivity: is the wetland managed with control structures or pumps? If there's a water level control structure at the inflow of this wetland, you might not be able to pick up on that from a remotely sensed image. Maybe it's indicated in a design plan, but the design plan might not tell you where those boards are going to be set up. When is the wetland ever going to flood, or is it going to be closed to the landscape? And then really importantly, what kind of drainage area feeds into that wetland? Is it a large area? Is it a small area? Is it mostly forested and not a big nutrient source? Or is it mostly agricultural and a known nutrient source? These are all really important features. And these are some axes that we think about, some of the features of connectivity when we say that word that we mean. So today, the specific results we're going to share with you are a case study related to connectivity. Postdoc Kenny Anderson is going to tell you stories of 3 H2Ohio projects. These are some from the early days that were completed, and we've been monitoring them for at least a year. And they really highlight the importance of considering connectivity when you're quantifying nutrient load reduction. The 3 projects are, if you're following along with your H2Ohio project map, they're numbers 11, 17, and 60. 11 is the St. Joseph's River restoration in Williams County. 17 is the Forder Bridge floodplain reconnection in Paulding County. Both of these projects were implemented by the Black Swamp Conservancy. And then finally, project number 60 is the Burntwood Langenkamp Conservation Area. And this is a project associated with the Grand Lake St. Mary's system. So now Kenny is going to tell you some neat stories about these wetlands. Take it away, Dr. Anderson.
All right. Thank you, Lauren. Hi, everyone. So I'm going to talk to you guys mostly about nutrient loading. Oops. Okay. Mostly about nutrient loading because the load of nutrients that goes into a wetland is, to kind of reiterate what Lauren was saying, the maximum amount of nutrients that it can retain, because it's not going to be able to take up more than it actually gets. And when you're calculating loading, the actual formula is just the concentration times the volume. So there are 2 things that you can modify to increase the load that your system is getting. Either you can have more water, or you can have more nutrients. And just to illustrate that, I have these 2 scenarios. If you have low concentration of nutrients, multiply it by a lot of water, these 2 together, you get 10,000 milligrams. You can also get the same number by having a high concentration of nutrients and less water. So I'm going to show you guys these couple sites that kind of exemplify these different methods, and then show you one more site that kind of shows when we don't know as well what's going on, what can happen. So the first one is this Burntwood Langenkamp Wetland Conservation Area. This map here is the drainage area of the Burntwood Creek. It flows kind of eventually into Grand Lake St. Mary's, and a portion of it is captured by the Burntwood Langenkamp wetland that's in this kind of blue box here. At this site, there's a pump, so we're actively pumping water into this wetland, around 155 million liters every year, and it flows through the wetland, then goes out. The concentration starts at about 0.35 milligrams per liter. It's fairly low concentration, at least compared to the next site I'm going to show you, and the site retains around 47% of the phosphorus that it gets. So take a look at this map right now, just so I can show you the next one. And you can note the difference in scale. That's about a mile on that scale bar. This second site, only 0.2 miles, a bit zoomed in. The actual parcel boundary of this site, the St. Joseph's River Restoration, is about the same size as Burntwood Langenkamp. But the area that it drains is much, much smaller. It's primarily just getting water from these 3 tile-drained fields, and they are actively farmed. So there is a high concentration of nutrients, but a lot less water than Burntwood Langenkamp. But these wetland pools have a large capacity to hold on to water after storm events. And because this site is able to hold on to this water for longer, there's more time for those kind of internal processes that Lauren mentioned to retain and suck up this phosphorus. So there's a higher percentage of phosphorus retained at this site that's just getting passive drainage, especially during storm events. That's where the majority of water is coming from at this site. So to compare the two, you have this actively managed site that's getting water pumped in from this much broader drainage area that has lower concentration because it's this broad area. It's a lot of different landscape that's feeding water into this system. And it's retaining a lesser proportion than St. Joseph's Restoration, which has more time for the water to sit, more time for it to suck up this nutrients. And it's starting with a higher concentration with less water going through the site. And it's passively managed. It's just water running off of these farm fields, mainly during storms. And so when you're thinking about kind of like your sites, building these sites, there are a couple things that you can think about. One is the watershed, the drainage area of the site, like I was talking about with Burntwood Langenkamp having this subset of an entire watershed, whereas St. Joe's has just these 3 specific farm fields. The wetland size, which kind of influences its ability to process those nutrients, specifically through the residence time, the amount of time the water kind of stays in the system, which is shorter for Burntwood Langenkamp, longer for St. Joseph's Restoration. And also just to show you guys, these sites are pretty much the same size. And overall, they retain very similar amounts of nutrients based on our estimates. They're just doing it in very different ways because of the source of water that they're getting. Burntwood Langenkamp is actively pumped. It's consistently getting this water in, whereas St. Joseph's Restoration is passive, and it's relying on this tile drainage that brings in high concentration nutrients with just a medium volume of water, primarily during storm events, whereas Burntwood Langenkamp is set up to get high volumes of water at lower concentrations. And Burntwood Langenkamp is retaining less, but overall gets more nutrients, so we come out with a very similar nutrient reduction values for these sites. And so when we're thinking about connectivity, estimating things like this are really great in theory, but it's much harder to do in practice because normally what we're doing to estimate the connectivity is GIS-based approaches, things like USGS StreamStats, digital elevation models that's just mapping out kind of the topography of the landscape and where water will flow downhill, and things like USGS Sparrow water quality modeling. And all of these kind of combine the drainage area of the site based on the topography of the landscape and rainfall to estimate how much water a site's going to get. But there are problems with scale with this approach, and I'm going to give you an example here. So this little image, this is from USGS StreamStats. Basically how it works is you take somewhere on the landscape, you click, and it'll show you all the area that is upstream from that point. So here we click this little kind of blue dot that's right at, this is the Burntwood Langenkamp site in this blue square. And this is the entire Burntwood Creek. And the site, again, is just getting a portion of that. So this works really great for understanding the drainage area, but you also need to know the pumping rate to know actually how much water this site's going to get. But then if you have something like the St. Joseph's Restoration, where it's much smaller scale, if you remember the difference in scale between those maps I showed you, you get something like this, where this is a zoomed in version. This little blue dot is where we clicked, and this is the drainage area that it showed. Whereas this is the site parcel boundaries in dark gray, and these are those 3 farm fields that are the primary sources of water for the site. And the reason we're not getting them in this drainage model is because all this flow is through tile drains. It's underground, and you can't detect that based on the topography. And these kinds of sites, especially these passive water delivery ones, where a boots on the ground approach is really valuable, where someone actually seeing the site, especially during storm events where the water is actively flowing, is really useful. And so this last example I'm going to give you is just to really highlight when this boots on the ground approach is really valuable and how it helped us out with the Forder Bridge restoration. So this site has passive water delivery. It is very storm driven. It's similar to St. Joseph's in that way. This is just to kind of illustrate how storm driven it is. This is the same pool, just 1 month apart, completely flooded in May 2023, completely dry just a month later in June. And so here's the site. The site is in this kind of dashed line. This is the parcel boundaries. This is the actual treatment chain wetland where the water flows through. And so based on the kind of like plans for this site, this area outlined in orange is the drainage area. And we also confirmed that with the digital elevation model using really high resolution kind of surface data. So we initially predicted that it was draining these 160 acres. And based on that, and based on using rainfall and the amount we expect would run off, we predicted 27,000 meters cubed of volume running off through this farm field, this little bit of forest, and this northern farm field, through this culvert and into our site. And with that, from this period, April to July 2024, I'll tell you why in a second, that period specifically, we estimated a load of 9 pounds of phosphorus. So again, that 9 pounds isn't necessarily what it's retaining, but is the maximum that it can retain because it's what it's getting. But then the problem was that Bob and Jenna, two of the people who on our team who are actively monitoring this site, they talked with some people from the Soil and Water Conservation District in Paulding County. And the people there said that they've been out there when it's raining, they've been out there when it's actively flooding, and they actually think it's only draining this small northern field and this little bit of forest, and that there's a culvert that we didn't know about completely outside of the boundary of our actual project that's draining this whole southern field. And so at that point, we weren't sure, should we just trust their word on this? Is it going to be draining this entire southern field? But that's where our sensor system came in really handy. So what we did was we set up our sensor system in this treatment chain and measured the water level in these pools. And based on the increases and decrease in water level, we estimated how much water was actually moving through the site by directly measuring the water. And with that method, we found 1,900 meters cubed of water was going in through this period of April to July 2024. And I have this period because April is when we first installed our sensors at this site. So that's when we first had data that was directly measuring the water there. But what this really showed was that this boots on the ground approach was much better at predicting what was actually happening at the site than these high resolution digital elevation models, because there are these features that are subsurface features that are man-made features that we can't detect just based on the topography of the sites. And so what that led to is us thinking this is the real drainage area of the site, this smaller northern field. And in our 2023 annual report, reported that between 4 and 45 pounds of phosphorus were being retained by the site, with 4 corresponding to this smaller drainage area and 45 corresponding to the full thing. Because at that point, we weren't sure which it was. And our sensor data, now that we have it, really shows that it is 4 pounds of phosphorus. And one other thing I want to point out before I move on to the next slide is the concentration of this site also could have given us a clue there, because it is relatively low compared to like St. Joseph's, which also we predicted was tile drained. So it's not, this drainage area isn't just affecting the volume of water, but also the concentration, because this full one, we expected it to be mostly tile drained farm fields. Whereas the smaller one, it's about half forest and half this farm field. So that has a big impact on the concentrations that you're getting too. So comparing our sites now, Fordor is draining less than we thought. The residence time is long, but because it's not getting this load of nutrients, it's limited on the amount that it can actually retain. And that's really important to understand, especially in these passively driven sites where you're not actively bringing water in, where you're less worried about concentrations. And again, both the nutrient concentration and the volume were affected by our understanding of where this site is actually draining. And we really had this valuable use of people actually physically seeing the site, having boots on the ground. And so then I'll turn this back over to Lauren to wrap this up.
Thanks, Kenny. All right. So what we hope that case study demonstrated is just how important thinking about connectivity is in this context of adding up pounds of phosphorus and targeting nutrient load reduction. The ability of a wetland to retain nutrients is affected both by how it's connected to its landscape and to those processes that happen inside the wetland. arguably its connection to the landscape is in some ways even more important than the processes occurring within the wetland, if you're thinking about it from this budgeting standpoint. But what we have noticed from early on when we talk with the DNR and we talk with some of our partners is that a lot of the plans and the designs for different wetland projects, when they're under development or when decisions are being made about them, this connectivity piece isn't always really considered to the level of detail that helps us predict accurately the amount of phosphorus that a given project is going to retain. And that's really important when we're thinking about distributing resources between things like cover crops and conservation ditches and this whole menu of options when trying to make really science-based assessments of how to distribute those resources towards this goal. So that was kind of our main take-home point for this webinar, was to help distribute this message to individuals who are making decisions about wetland projects, designing wetland projects. If your project is aimed at nutrient removal, you cannot ignore connectivity. Now, it makes sense that past projects did not explicitly include connectivity, drainage area estimates, nutrient load reduction estimates in this quantitative way. And that's because in the past, a lot of the existing wetland restoration programs and incentive structures have really been focused on just getting wetland acres back on the landscape, rehabilitating, creating healthy ecosystems, creating viable habitat for waterfowl and plants and pollinators and all of those other ecosystem services, with kind of the underlying assumption that wetlands are also going to be effective at water quality improvement. Well, now we've had this big shift. It's a bit of a paradigm shift in not only thinking about wetland habitat and healthy ecosystems, but almost treating wetlands as water quality infrastructure, right? Natural infrastructure, leveraging the natural ability to filter water. And that requires a different approach. Now, one open question that we hope the monitoring program is helping to address, and we think it's possible, is how do you invest in projects that achieve both of these goals? But within the context of the H2 Ohio initiative, the water quality goal is paramount. And so again, that means thinking about connectivity. So we've kind of thought about the different ways that designers and decision makers can enhance the kind of connectivity that helps you remove more nutrients, helps meet those higher nutrient load reduction targets. So here's a quick list of tips to quantify connectivity more accurately to estimate nutrient load reduction. One is, if you are using a digital elevation model to estimate the drainage area of your site, use the most accurate topographic data that you have and use appropriate tools. Understand when Stream Stats is an appropriate tool that's going to give you a reasonable estimation versus when maybe the scale is too small or the nature of that specific location is not going to be accurately captured by using a tool like this. Know when that kind of cryptic connection, drain tile systems, sewer sheds are going to be more impactful to the way your wetland is connected to the landscape, and solicit that on the ground knowledge ahead of time if the goal of the wetland is to remove nutrients. If there are water level control structures or any kind of pump management in the plans, we see this in a lot of wetlands. There's a lot of coastal projects where water level control structures and pumps are being built without a lot of detail about how those structures will be managed. When you put a water level control structure at the outflow of a wetland, a single decision about adding or removing a board can completely change the net function of that wetland from a budgeting standpoint. So if you're submitting plans or considering plans about a wetland for water quality improvement that have structures like this in place, those plans have to go hand in hand with the description of how those will be used to manage the hydrology of the site, even if it's going to be a set it and forget it passive system where the structure is in place only in case of maintenance. That's really important to consider. And then one kind of feature of connectivity that we didn't get to describe in as much detail is systems that are more of a floodplain or side channel type wetland that are designed to flood when an adjacent body reaches a certain level. There's existing topographic information and existing hydrologic data and modeling approaches that help you estimate how frequently will that site flood. Based on that frequency, how many storms will it capture? How many pounds of nutrients will it remove? It takes a little bit of extra work, but there are available tools to do this. We have some tools that can help people, anybody who wants to dig more into our results, think more about our monitoring framework and how that might influence and improve wetland designs. First of all, I mentioned our newly updated monitoring framework. This includes a lot of background information. So especially if you're new to the field and logging in, you're like, I just got hired and I'm learning about wetland biogeochemistry. We include background information about the biogeochemical processes that I wasn't able to describe in detail during this talk. And this is also a really good overview of the structure of our monitoring program. We have now compiled and documented many of our protocols for sampling and water quality analysis and data processing that if any individual doesn't want to reinvent the wheel and develop their own monitoring program, these are all available by request. We have created some case studies that are sort of bite-sized selections from the long annual report that are each focused on 4 or 5 specific H2 Ohio projects and the results that we came to from our 2023 data that are available for download at this website. They're nice little printable 2-pagers that are actually 3 pages. And of course, our annual report that I've already plugged, and all of the past public webinars that we've given and several other recorded webinars are available on this site. If this is the first time you've logged in and you feel like you missed some of the background information, those are great resources. What are we going to do next, right? This is our update. So we collected a lot of great data in the 2024 water year. And so right now we are actively compiling those data sets so that we can summarize them and analyze them and prepare an even better annual report for 2024. So stay tuned for that in spring 2025. Some of these projects, we might end up with 2 data points, the 2023 load reduction and the 2024 load reduction. That is so exciting to me. It's the beginning of a long-term monitoring program. We're also going to keep monitoring these projects. So we're currently finalizing our plans for monitoring in 2025. We're going to continue monitoring 34 of the projects that we've been monitoring. We're going to start monitoring 3 new projects. And then there's 12 other projects on our radar that we're going to characterize and evaluate for future monitoring. So starting to collect some data. We have data sets, the data that was used for the 2023 report and has been embargoed for a year will be published and released and publicly available for anybody who wants to download and analyze the data for themselves. And a couple of really exciting kind of bigger picture initiatives is you see all these dots on a map. We, even with a really robust funding and a really robust team, are only so many people, and our boots are on the ground in only so many places. Many of these projects are 3 hours from the universities where we have our labs. So we have hired a full-time outreach and engagement coordinator, Sienna Larrick, who's going to help us enhance our capacity to monitor these sites through leveraging community-based participatory volunteer sampling. And we're partnering with organizations like the Cleveland Water Alliance to help us do that. So stay tuned for more invitations to participate in that kind of work in the future. And then also I mentioned a little nugget earlier on about water level control structures and pumping and how decisions made can greatly impact the functioning of a system. So we have started collecting data on management action. So when a manager makes a decision to change the water level in a wetland, if we know why and when and how they did that, it really improves our ability to synthesize the data that we're collecting. So we're hoping in future years to expand our data collection. We've already built some great tools to help empower that, and then share data with individual managers in ways that we hope is useful to you as a manager. And honestly, so much more. There were so many stories that we didn't have time to tell in this webinar, so many excellent questions that were submitted that we were not able to answer during this slide deck. But luckily, now I think we have time to answer some of those questions and to answer some questions that might be coming in live through the Q&A. And in case we don't get to them, here's the contact information. So if you have questions about the wetland restoration, I have a project I want funded, what does the ODNR want to do? Email h2ohio@odnr.ohio.gov. If you have questions about what kind of data do you collect, what does that nitrate concentration mean? You know, what is geophysical data? h2ohiowetlands@kent.edu is your go-to.
Lauren, thanks for that. I think
Yeah.
I have a bunch of pre-submitted questions I'm looking at, and also some that have been coming in. Thank you for those engaging in real time. But Eric, I thought I might come to you, see if with being the program lead for this for the DNR, were there any thoughts or comments you wanted to articulate before we dive into those questions, sir?
Well, I appreciate the opportunity, Chris, and I'm disappointed. I want to keep on learning about our wetlands. Can we just tack another hour onto this, please? This
I got a whole bunch of extra slides at the end. I'll bore you if you want.
Awesome. Let's do that Friday.
Cool. Sounds good.
I and my team, we're in charge of the implementation end, and I guess I would just add a quick coda. I want to make sure we do have some time for questions, but just to emphasize the significance of what you're hearing from the monitoring program to us on the implementation end. In 2019, when we kicked off the H2 Ohio program, we had a decision to make. There were two routes we could go. Do we spend the next 5 years building a perfect program on paper, filing a report? It's not really the H2 Ohio way. The other route is to let's restore 17,000 acres of wetland and associated habitat, and let's dedicate serious monitoring funding to that, and get the best people to do it. I think you can see we have the best people doing it, and learn, pun intended, from what the monitoring program is telling us. So, we kind of look at what's coming our direction from the monitoring program in terms of past, present, and future H2 Ohio. In terms of the past, in terms of completed projects, we're looking carefully at those management considerations that come out of the annual report. Where the folks who now know these projects better than us are telling us, what do we need to go back and maybe fix? We're looking at two projects with Hancock County Parks. Shout out to them. I don't know if they realize there are guinea pigs with this, but they are. And we're talking about trying to fix some projects from a water quality standpoint to make them perform better. And we're adjusting our expectations on some of the early projections we made on projects based on what we're learning. In terms of the present, we have an ODNR H2 Ohio engineer who is translating these monitoring results into comments on 30% design plans for ongoing projects. Making sure that what we've funded is going to best meet our expectations based on the best available science. And then for the future, it's incorporating these program findings, these monitoring findings into project prioritization. And we've had the help of a subset of the monitoring program actually review and provide feedback on proposed projects. And that's incredibly helpful. As for the future, we're looking forward to adding more data points and understanding in an even more carefully constrained way what design considerations, what wetland siting protocols we need to emphasize in our funding decisions. I'll leave it at that. I want to make sure we have time for questions.
Eric, that was great. Thank you very much. So I'm going to dive into the questions right away. And we've seen one that was submitted prior to the webinar and also twice here on the webinar. So definitely an important ask. And so Peter, thanks for engaging through that. The question really is about source sink dynamics, right? So we know that these wetlands are going to, in many instances, as you saw, draw down some of these nutrients. But they can't do that indefinitely. And so what do we know about the effective lifetime of these wetlands that we're constructing? So maybe Kenny, take a stab at it, or anybody on the wetland monitoring team.
Yeah, I've got that. So one of the things that I've been working on, we've been doing kind of an extensive literature analysis, looking at what kind of data there is that already exists on like long-term wetlands and how long they retain phosphorus. And one of the things we know is that there is very little data on that. And that's one of the real benefits of this program, if we're able to get long-term data and really start understanding what causes a wetland to retain more or less phosphorus over time. But what I can tell you from the few examples that are out there is that wetlands can continue retaining phosphorus for a long time, at least decades, if not longer. There are ones that are like 30 to 50 years old reported in the literature that are still retaining phosphorus. And I think the mechanism for that is somewhat clear, because one of the main things wetlands do is that they build up sediments. And the more sediments you have coming in is the more potential places for them to absorb phosphorus. And they're also building sediments through vegetation, because vegetation is growing, taking up phosphorus, dying, and then burying it in the soils. So one of the things is potentially a wetland could keep retaining phosphorus until it just stops being a wetland because there's too much sediment there. But we don't know kind of the drivers behind that or how long that could potentially go on. And that's one of the benefits of what we're learning from these sites.
Thank you, Kenny. Any other thoughts from the team here?
I'll just add the source side of that equation. We know from past research that there are time periods when just the phosphate can become desorbed and mobilized from the sediment based on just like a body of research and all the things anecdotally that we're seeing in our data and in the field. It seems like if that happens, it's transient, and the total amount of phosphorus that might be released is a lot smaller than the total amount that's retained, especially on sediments. And that it's really only going to be released if that happens when the wetland is flowing into a downstream system. So on the source side, it is something to be aware of and continue surveilling for, but it seems rare and not impactful, at least on an annual budgeting timescale.
Lauren, thanks for that addition. I'm actually going to put Sienna on the spot. So Lauren mentioned Sienna as one of our, our community engagement team members now. So there's a question that came in. Says the H2 Ohio program has a lot of stakeholders, which include farmers, companies, general public, even government officials. With that said, what helps get those stakeholders to care and get excited about H2 Ohio? So what approaches have we taken to reach and talk to those communities to spread the positivity around H2 Ohio? Sienna, putting you on the spot here.
Yeah, so I love this question because stakeholders and positive engagement with H2 Ohio and with the monitoring program is pretty much my job description. And so I don't think it came up in this webinar, but if you've tuned into the monitoring program in the past, you've probably heard Lauren or somebody else say that each wetland is a snowflake, and usually they're talking about that in the context of the science. But because of the way the H2 Ohio initiative is designed, that's also true with the stakeholders and the communities and the different kinds of engagement that we can see with these wetlands. And so I can't sort of answer across the board, so I'm going to give an example of one that's really stood out to me as I've been stepping into this role, and that is the Otsego Schools Fox Shank Living Laboratory. It's a very long name. But from the, function side, it's a conversion of a farm field, which we've seen with a lot of other wetlands, but it has this really unusual situation where it is a partnership between the Black Swamp Conservancy and the Otsego School District. It's located across the street from the school. And because of that, we see this really amazing engagement from the school where it is treated as sort of an outdoor classroom. You get this really hands-on experiential learning. Also, some of our participatory sampling activity that I'm focused on in my role as well. is being developed there with the support of Black Swamp Conservancy. Um, but it's also just a space that the school is able to bring students not just in the science context out, but in an arts context and, you know, in an industrial arts context. And I had the opportunity to be on the ground and talk to one of the educators, and she was, you know, expressing that her students are out there, they're, you know, they're water quality sampling. But they're also just saying, you know, this is so relaxing. I wish we could spend more time out here. And so on a very qualitative level, I often joke that wetlands needed a better marketing team a little bit historically. And, you know, the H2 Ohio initiative and the monitoring program are doing a little bit of that legwork, exposing people really positively to, you know, wetland environments, to science-based monitoring, and to you know, the water industry in general. So that's kind of one of those facets of how stakeholders can really get energized and engaged through this program.
Thank you, Sienna, for that. I'm going to come to another one that came in. I love this question. So it's asking, I mean, the presentation you heard now is once that site is built, how do we build connectivity within that site, right, to get more bang for our buck? But the question's coming in and asking about criteria we would recommend for targeted siting of treatment wetlands. So how do we, with what we've done here, and I know it's one of those stories that we didn't have enough time on the webinar today, but how do we even figure out where to start thinking about putting these? Not even just the connectivity within the wetland, but how do we site these things? So either Kenny or Lauren, weigh in on that one if you could.
So my quick answer to that is I think it's still an open question, and I think there's a couple of different approaches that could be taken. But with the new knowledge that the Wetland Monitoring Program is providing, those sort of watershed scale questions can be addressed with more information. So there's existing modeling frameworks and sort of map-based frameworks to prioritize locations for wetlands based on, is the soil type already hydric? Is it likely to support a wetland? Is it likely to have been wetland in a past? And I think that some of the actual empirical budget measurements that we have been able to generate from our data can help feed into some of those modeling approaches to give actual quantitative assessments and quantitative aspects to those different kinds of scenarios. We're actively pursuing more engagement with some of the groups in Ohio that are already funded to do different watershed scale modeling to run those different scenarios. But I think in a really broad sense, connecting it to a nutrient source is step one. So when you're downstream of a tile, you're getting a lot of nutrients. It might not be a high volume, but it's high concentration, like Kenny showed. If you can put a lot of wetlands downstream of a lot of tile drains, that might give you a lot of bang for your buck. When you're adjacent to a large river that's carrying a lot of nutrients, maybe at a lower concentration, but something like the Sandusky River or even a mid-sized creek like Burntwood Creek, if you can get a lot of that water through a wetland, then you're also treating a lot of phosphorus. So it's just shifting from thinking about, you know, let's plant a bunch of plants and take up the nutrients. That's great. They need to have nutrients to take up. So I think that's just a really broad brush answer to the question.
I want to tack on one thing just real quick. I think one other thing to consider about that is also the size of your wetland, because the bigger your wetland is, the bigger like volume your wetland can hold is the more volume it can treat. Because also that like residence time aspect, you need the water to be able to sit in the wetland for some amount of time. So I think a lot of it's dependent on the size of the wetland too.
So we've only got 2 minutes left. So I'm gonna have Eric, this is kind of more for you, but it was a submitted question. And one is, how long do you monitor a H2O project for? I'm gonna leave that on the side, but the question is, how do we determine success? And then the second part of this question is, how often is a project altered or renovated for a better outcome? And so, Eric, I think those might more resonate with perhaps you, and we'll probably close it down after that. Some of the questions that folks have asked have been answered online, so please check the Q&A. But Eric, coming to you, how do you determine success, and how often have you seen projects altered or renovated?
Yeah, well, you know, we have our I Heart Wetlands stickers at ODNR, and we love the idea of 17,000 acres of wetland and associated habitat restored. However, what's happening at the Waterville Gauge on the Maumee, what's happening in the western basin of Lake Erie, is really at the forefront of our mind. That's why we're doing this. And so we determine success when we meet our objectives in that regard. We are about the journey and the destination with H2O. We like both of those things, but it is ultimately, how we're affecting water quality change and how our individual wetlands stack up to a cumulative number there. We're in the process of evaluating about 5 completed wetlands right now for specific alterations that we can make to those wetland systems. We're ready to move forward on one of those. Ready to start design on another retrofit. We're still evaluating a couple more, but we'll continue to make adjustments on wetlands as long as the management considerations guide us that direction, and our partners are willing to work with us on that.
And maybe we're at 1 o'clock. I'll point to Peter's question and answer. Maybe it sums it up. Basically, the walkaway point is it's complicated. And so basically the work that's being done here clearly is shedding light on the answers that are needed to bring the Maumee River watershed to where it needs to be. So stay tuned. We plan on doing these annual things as long as we can, but lessons are being learned, and I think we're making progress, but it is very, very complicated. Thanks to Kenny and Lauren for your presentations. That was great. And thanks to, of course, the Governor's H2 Ohio program and the DNR for being the momentum behind this in the first place. So thanks, everybody.
Thank you.
Thank you, everyone.